My name is Christoph Sentner. I'm with the University of Würzburg, and my advisor is Alexandra Dimitrenko. And today I will present our joint work with the UC San Diego and the TU Darmstadt with our paper, Smarter Contracts. Now, first off, as the title says, we are looking into the security problems of smart contracts. Now, if you follow the news or read news articles around cryptocurrency and such, you will find news articles such as that crypto scammers steal $14 billion. You find that crypto hackers steal $2 billion. And even some stupid bugs lead hackers to steal $31 million. And now also the FBI warns users that scammers might steal their money from cryptocurrency projects. Now, those are all security problems with smart contracts, but first we want to look at the basics of smart contracts. What are those? So what are smart contracts? So smart contracts are software programs hosted by blockchains. I hope everybody knows here what blockchains are. So what do those smart contracts actually do on the blockchain? They manage financial assets, for example, the cryptocurrency on this blockchain. How do they do this? They upload their code and they have an account now with a balance of some kind of cryptocurrency, and this code automatically manages this account. Now, as you've seen before, they are in charge of a significant amount of financial assets, meaning they are pretty attractive targets for attackers to steal from. And even worse, since blockchains are public, so are also the code segments of those smart contracts, which leads to detection of vulnerabilities in those from the attacker. Now, in our case, we also focus on Ethereum, as it is the most prevalent one that uses smart contracts in blockchains. Now, we want to look at the vulnerabilities at a selected number. Now, the vulnerabilities in smart contracts are software-based, for example, which also happen in other software. For example, integer under an overflow, when integer flips if it's iterated too much. More a runtime issues, where those vulnerabilities are based on how the smart contracts are executed. For example, reentrancy, where the attacker abuses external calls to drain funds. And also there are vulnerabilities tied to how the blockchain executes. For example, rig randomness. It's difficult to create randomness in smart contracts. All in all, there are many vulnerabilities, even more than I listed right now. And they are generally difficult to patch, since the Ethereum blockchain is immutable, and it makes the in-place patching very difficult. And this leads to an extensive need for security testing of those smart contracts before we deploy them or when they are on the blockchain. These security testings is also done by academia and industry. There are many, many tools out there to do exactly this security testing. However, generally, those are limited in scope, meaning they only target specific vulnerabilities. They are also limited in their detection capability. For example, a static analysis tools detects different vulnerabilities than a runtime analysis tool. They also, for example, runtime analysis tools have poor efficiency. Some run very long, take a long time, or don't even finish at all for a smart contract. Most of them need access to source code, meaning we cannot test the bytecode on the blockchain directly with those. And even older ones have interoperability issues. For example, if the compiler version changes, or some tools need a specific version of Solidity to actually work with the testing. So our basic question was, can we combine all these tools into one and alleviate some of the limitations, for example, the limitation in scope and the limitations of the different detection capabilities? Our idea here is to use one machine learning tool that learns from many other tools, and not just the tools that are now available, but also the tools that will come in the future. And we call this tool Escort. Now for Escort, we split it up into three phases. The first phase is a training phase, The second phase is the transfer learning phase. And the last phase is where we deploy our model. For the first phase, the training phase, we use the existing vulnerability detection methods, learn from them, and are then able to create a model that detects them. Once a new tool or a new method for vulnerability detection is available, we can use transfer learning to learn from this new method and incorporate it in our model without retraining everything. In the deployment phase, we use our model to efficiently and effectively detect all the vulnerabilities in one scan. This idea faces some challenges. So first, we want an effective detection. The effective detection, we use deep neural networks, which shows promising results in other domains. We want to detect different vulnerabilities in one tool. And for that, we use a multi-output architecture, which we go into in detail later. We want to be extensible to new vulnerabilities. And for that, we leverage transfer learning, which allows us to add new vulnerabilities without retraining the whole model. We want to learn in minority classes, since deep learning generally needs a lot of data to actually perform well on minority classes. Here, transfer learning has another great feature, which allows us to learn on those classes. And last, we do not want to be dependent on source code. And for that, we focus on the bytecode. Now, how does our approach look for the multi-output architecture? How do we do this? First, we have our bytecode, which we input in our so-called feature extractor. Here, we extract specific features of the smart contract that indicate some vulnerabilities, for example, call statements. These features are then forwarded inside branch layers, where the actual decision is made or trained which vulnerability type that is, for example, a reentrancy type. Those vulnerability branches are the number of vulnerabilities we want to detect. Now, if you want to take a closer look at how we did the feature extractor, we have here used the approach of natural language processing, where we include an input layer that feeds an embedding layer that learns from the bytecode and represented it as numbers. And with those, we learn the representation of the bytecode. Now we have another point where we want to use transfer learning. How do we do this? We take our model or our architecture from before, which is already trained, and freeze the weights, meaning we do not train again those weights, but we only train on the new vulnerability branch. So we take new bytecode, new labeled bytecode via another method, train only our new branch for this vulnerability type, and leave the rest as is. Now for training, we of course need data. So we need labeled data, labeled bytecode. How did we do this? For our data set, we crawled 3.6 million smart contracts and labeled them with 4 vulnerability tools. For the crawling, we used 3 tools. Google BigQuery, which is basically a database for bytecode. Geth and Ericon are blockchain clients that allows us to download the blocks that include the bytecode of the smart contracts. We then download those and save it in an intermediate database. From this, we need to pre-process this bytecode to be actually included in our machine learning approach. And for the labeling, we use our vulnerability scanners. Now here, this was rather difficult since those scanners are generally not designed to be scalable, especially for 3.6 million smart contracts. And once we made it scalable, we also needed to run it to actually detect those labels. Once we have them, we combine our pre-processed bytecode and our vulnerability labels in our database. Now this labeled data, we will also make public for other research. Once we have our data set, we create our data sets for learning. Here, after cleaning up and deduplicating our 3.6 million smart contracts, we have around 280,000 instances of smart contract samples we use for our training, for our evaluation. The first part in our data set is the main training phase, where we have per vulnerability class around 60,000 samples per vulnerability. We then also have an extension data set for the transfer learning approach to test it, where we have around 20,000 samples for vulnerability. We also want to test minority classes, and for that we have an underrepresented data set where we have around 1,000 samples per vulnerability class, just to show if we can perform on minority classes. All in all, we'll use here 3 vulnerability tools, labels from those tools to do the training. And for the training, we have an 80% training split, 10% validation, 10% test split. Now for the evaluation, what are our results? We have here our results for the main data set, for the transfer learning data set, and for our minority classes. We can see that we have an F1 score for our main training of over 97% for all the vulnerability classes. And for the transfer learning with 20,000 samples, we have 94 and 95% F1 score. And for our minority classes, we also have great performance with an F1 score over 69% for each class. So now we have a detection tool that can detect all the 11 vulnerabilities in one scan. And we have an efficient inference with a custom GPU that does the inference in 0.2 seconds. We also did a ground truth analysis of our tools to compare our tool Escort with the tools we use for labeling on a ground truth data set. And for that, we started actually thousands of different security audits where auditors checked smart contract projects for vulnerabilities. And this resulted in 373 smart contracts that are available, meaning the Git repositories are still there. They are actually compilable, and they are relevant samples for vulnerability classes. As a result, we see for the different vulnerability classes that we have comparable results to the underlying tools. Most notably, we have for reentrancy even a better result than the underlying tool. And for the unchecked calls, we have a worse results. After looking into it, we saw a change in programming from the developers that led to a bias in our data set in that sense. So in the conclusion, we presented a DNN-based vulnerability detection approach to detect multiple tools with to combine multiple tools into one tool. Escort is the first framework that is by design extendable to new vulnerability types. We show good performance across all vulnerability types, especially the minority classes. We operate directly on opcode, meaning we are independent from decompilers. And we have a very good inference time. For future work, we want to look into how minority classes can even be lesser with the effectiveness of transfer learning and finding the vulnerabilities in the bytecode, not just checking if the bytecode itself is vulnerable. Thank you.
So I wonder if Escort can detect 0, 8, what is that or not? No. Okay, so a different question maybe not related here. I mean, if you have a smart contract which is already have a vulnerability already deployed, how this can be we in our paper we actually addressed it in the way that we looked at how users interact with smart contracts, for example, with distributed applications. And here there is a tool called MicroMask, which is basically a wallet that allows you to connect. And we included an Escort in there to show the user that the smart contract they're about to interact has a vulnerability. So we cannot remove those smart contracts, but we can show before interacting with it, there's a problem. Other questions?
Hello, and thanks for the talk. So my question is, imagine that tomorrow there is another static analysis tool that comes up with a new type of vulnerability, and then I want to integrate that into Escort. So what would be the process? what is needed to integrate new kind of vulnerabilities into machine learning?
As I said, we need samples for that. For our sample base, we did not use augmented data, or we didn't generate them. But if you want to be fast and integrate them, you could generate multiple smart contracts and train on them.
Other questions? So,
very simple question. I mean, you assume that you don't have access to the source code, right? You use only bytecode. So, what if you have access to the source code? I mean, how this would change this code will to make it more efficient? So, really have any impact?
Yeah, so the problem is with source code, I mean, the simple solution would be to just violate the bytecode, but that will remove some information. So Escort is designed to detect vulnerabilities in bytecode. If you want to look at the source code, I would suggest to use actually other methods for machine learning.
I have a kind of a different question. So your model Escort, actually, as you said, you have new detection techniques come out, you integrate them into your model, right? Let's say that there are vulnerabilities which are no longer relevant for whatever reason, right? They're patched, the client is patched so that it exits. How do you modify your model to remove those vulnerabilities? Because they will just give technically false positives, but they will just raise an alert.
Yeah, sure. I mean, that's actually.
Do you train the model?
No, you can just cut off the branch. So you know which branch actually predicts this vulnerability, and you ignore it or cut it off from the feature extractor.
Okay. So you would modify your feature extractor?
No, you don't modify anything. You just cut the prediction for this vulnerability type.
Okay, for that particular one.
Exactly. Yeah.
But what about if there's if there is a particular vulnerability in that type that is no longer relevant? So still.
I mean, if you have a vulnerability type, but bytecodes itself is still are relevant as they are bytecode used. So the feature extractor still holds the full information from this vulnerability class. The only thing you do not want is to have the detection at the end, basically.